Good evening, everybody. Welcome to Turfgrass Epistemology. My name is TravisShaddox. We're going to be going over fertilizers tonight. We've been doing fertilizers for the last couple of weeks, and tonight will be the last night that we go over fertilizer formulations for a while. We're going to be going over relatively advanced formulations tonight, so this may be an episode that you want to pause and work through some things and come back and listen to them 10 or 15 minutes and pause again, because there's just some formulations and ways to build fertilizers that require a fair amount of mathematics. And tonight is that night to introduce it. So don't be afraid to pause it and, come back when your mind is in a better space, because some of it is rather complicated. So, that's what we're going over tonight. We're going to be doing some multi-nutrient raw materials tonight. And then we're going to be going over filler. There's about 10 or 15 minutes. I want to go over different types of fillers and how to formulate with filler and how to formulate to avoid filler. And then at the end, we're going to reverse formulate 3 fertilizers. And I've intentionally chosen some relatively difficult fertilizers to reformulate so that you can see how it's done. And then whenever you need to do it, it's probably going to be much easier because you'll see when we get there. So you can't always reformulate everything, but most sort of normal blends you're going to run into, if you're curious what's in it, then you can follow the procedure at the end and get to that. I was going to show a video tonight. I'm not going to do that. Somebody commented in one of my videos and linked a video that is so, it's so bizarre. I think it's fake. I don't think it can be real. It has to do with I haven't watched the whole video yet. Actually, I haven't even watched the video. That's the reason I don't think it's real, but I hesitate to say anything. I'll watch it and then I'll go over it in a future episode. But the video apparently shows a well-known YouTuber talking about fertilizer burn and how it's a result of the actual physical temperature of the fertilizer particles. I don't want to say anything because I haven't watched the video yet, but that's what somebody commented to me on, and they linked the video, but I haven't had time to watch it. I can't believe it. It's got to be fake. So I'll watch it, and then I'll probably bring it to on the members only stream on Monday morning if it's actually legitimate. I can't believe it would be legitimate. That's got to be like an April Fool's thing or something. I don't know. Anyway, I was going to show that tonight, but I didn't have time to watch it. But that's like a little teaser for maybe Monday's member only show. Well, if it's legit, then I'll go over that video. But tonight we're going to be doing fertilizer formulations, and we need to get into it because I got a lot to get to. And I'm going to get through it one way or the other tonight. So after tonight, there's not going to be any more fertilizer formulations for a little bit. Welcome to the members who are in the chat. Gray Fox, Andrew Burris, Eric, Chuck, good evening. Brady, Mike Conroy, Gray. The closing music tonight is from one of my favorite bands. First band I ever watched live, actually. In 90, I'm going to say 90 or 91. It was a long time ago. Anyway, all right, let's get to it. Okay, formulating with multi-nutrient raw materials. Now, we've already gone over a couple of episodes where we're formulating fertilizers, which is blending the fertilizer together using raw materials like urea and sulfur-coated urea and muriate of potash and so forth. And you want to come up with a fertilizer like a 24012 or a 24211, whatever the analysis is. And we've been walking through how to do that, how to add in certain amounts of fertilizer based upon the guaranteed analysis of those raw materials to result in a finished product of a desired guaranteed analysis. So we've been walking through that and doing it relatively simple. We've been using usually every time so far, single nutrient ingredients like just urea, or urea has just nitrogen, potassium chloride has just potassium, and so forth. But there are many raw materials, and very common raw materials, that contain more than one nutrient. And when we do that, we have to account for the primary nutrient that we're blending with or we're formulating with. It's going to come with a secondary nutrient, and we have to account for that. So let's get into it. Formulating with multi-nutrient raw materials. The steps we're going to do tonight to do this through multi-nutrient raw materials is step 1, we're going to determine the total pounds of nutrients needed, i.e. multiply the analysis by 20, which is what we've been doing a single analysis, a single nutrient analysis. If it's a 10, 0, 10, you're going to do 10 times 20 is 200 pounds of nitrogen. 10 times 20 for the potassium is going to be 200 pounds of K2O. So the first step is just like the prior steps. The next step is to determine which materials contain multiple nutrients. So if you have concentrated superphosphate, you need to understand that that's only phosphorus. There's no other nutrient in there. But if you have diammonium phosphate, it has ammonium, it has nitrogen, and it has phosphorus. So you need to have some knowledge, or probably Google it. They'd probably find it, and understand that some raw materials can't be divided. You can't remove the nitrogen from the phosphorus because the molecule itself is diammonium phosphate. Okay, so you need to determine which raw materials contain these multi-nutrients. And then you need to formulate or start blending with the multi-nutrient sources first. So if you have diammonium phosphate as an example, and you have 24, 10, 0 or whatever, you need to formulate with the phosphorus first. You can't formulate the nitrogen component first. You have to formulate the phosphorus first, because the phosphorus, the only raw material you're going to be blending with would be a multi-nutrient source containing phosphorus. And then you subtract the secondary nutrient from step 3 from the total secondary nutrient required. So for example, I'll get to it. But so you add in the phosphorus, you're going to have some nitrogen that comes with it. You subtract that from the total nitrogen that you need before you formulate the nitrogen source component. And then you formulate the remaining nutrient. Okay, step 5. Okay. The question I'll answer this question, Mike. So Mike asks, why would you want a multi over a single nutrient source? It's not necessarily that you would want one. There are cases where the multi-nutrient raw material can be less expensive than either of the single individual ones. I'll give you an example. If you're just using urea and concentrated superphosphate, it's going to be a little bit difficult to find a less expensive version of that fertilizer using different sources other than urea and concentrated superphosphate. But occasionally, depending on the cost of the material that came into the blender, usually it's a FIFO, first in, first out. So depending on when that cost hit the raw material in the system, occasionally you might blend with diammonium phosphate, use the phosphorus, and then subtract the nitrogen from the total nitrogen you need to use from urea. And then the total at the end of the day might actually end up being a little less expensive than urea and concentrated superphosphate. Sounds a little bit complicated, but one reason why you might want to is because every now and then you might actually find it to be less expensive. In addition, other raw materials like sulfomag or sulfate of potash magnesia, I don't know really why you'd want to ever apply magnesium, but if you did want to apply magnesium, that would be another option or an example where you would apply magnesium from sulfomag, and it provides some potassium on top of that. And if that potassium was what you wanted already, the amount was what you wanted already, you wouldn't need to add any more potassium from a different source. So there's really not agronomically much of an advantage over using a single or a double. There might be advantages to using this raw material versus that raw material, but single or double, I don't know much of an advantage, but there sometimes can be a cost advantage. And there sometimes can be a blending advantage based upon your desire to eliminate waste. So some very high concentrated products like, let's take concentrated superphosphate. If it ends up having a lot of filler in there and you're trying to avoid that, or you've had problems with it in the past, you can actually blend with diammonium phosphate or monoammonium phosphate and reduce some of the filler that might have otherwise been included. So there's some reasons. They're not particularly strong, but every now and then there's a good reason to do it. Okay, so let's look at a 2510. In this example, you would formulate the phosphorus using DAP. So we're going to use a 2510 using urea, diammonium phosphate, and sulfate of potash. Okay, the urea contains only nitrogen. The diammonium phosphate contains nitrogen and phosphorus. And then, of course, the sulfate of potash contains only potassium. Well, it comes with sulfate too, but we're not going to consider that at the moment. So in this example, you want to formulate the phosphorus first because it's the only guaranteed element that is coming from a raw material that contains both nitrogen and phosphorus. So you need to formulate that first. Then you're going to subtract the nitrogen from that DAP from the total amount that you would otherwise have used as urea. Okay. Then you formulate the remaining nitrogen using urea. Then you formulate the potassium using sulfate of potash, and then you add filler to bring it to 2,000 pounds. Don't worry, I'm going over this quickly, but I'm going to show many examples of this. Remember, this is a relatively quick-paced show tonight because I've got to get through it because I want to finish everything up tonight on fertilizers. Okay, so this would be the example. Again, just pause the video if you need to kind of go over this and remember it because I'm going to be moving quickly tonight. When a multi-nutrient material is added to supply a nutrient, the second nutrient must be subtracted from the secondary total. So an example, 20, 10, 0 using urea and DAP, you're going to take the 20, which is the 20 units of nitrogen, you're going to multiply that by 20. And the reason we multiply it by 20 is because we're multiplying it by the number of pounds that are in a unit. And 1 unit is 1% of a ton, and 1% of a ton is 20 pounds. And we're blending everything on a ton basis, remember that, okay? So 20 units of nitrogen multiplied by 20 pounds in a unit comes up to 400 pounds of nitrogen. So that's going to be the total pounds of nitrogen that we need. Then we're going to take the 10 units of phosphorus, and we're going to multiply that by 20. We're going to come up with 200 pounds of P2O5, okay? That 200 pounds of P2O5 is going to be entirely derived from DAP. DAP is 46% P2O5. So we take the 200 pounds divided by 0.46 and we come up with 434 pounds of DAP. But in that 434 pounds of DAP, 18% of that is nitrogen, which is 78 pounds of nitrogen. And that's what you have to account for in multi-nutrient raw materials. You're going to have to subtract that 78 from the 400. So because DAP is multi-nutrient and the only P source, we first formulate the phosphorus from DAP. Then it comes up with 400 pounds of nitrogen. And then this 78 pounds is subtracted from the 400 pounds of nitrogen that we need. And now we only need 322 pounds of nitrogen because we got 78 from our phosphorus source as well. Okay, so 322 pounds of nitrogen divided by 0.46. Now this is coincidental that the 0.46 is 46% nitrogen from urea and DAP is 46% phosphorus from DAP. So it's a little coincidental there. This is not the same percentage. I mean, it's the same percentage, but it's coming from a phosphorus source or from a nitrogen source. Anyway, 322 divided by 0.46 comes with 700 pounds of urea. So those are all the raw materials we need. And then we need to put this in a whoops. Oh, I thought I had that. Oh, I thought I added it all together. I guess I didn't add it all together. But anyway, so you take the 434 pounds from DAP, and then you have 700 pounds of urea. You'll add that together, and then you'll subtract that from 2,000 pounds and add the filler. And that's how you would formulate a 20-10-0 using urea and DAP. Okay, so that would have a lot of filler in it. That would have 900 pounds of filler in it, basically. Pretty wasteful blend there, but that's just an example. Okay, so problem 3. After I read this problem, if you're watching this on a video, you might just pause the video if you want to work through it on your own, because I'm just going to read it and then work through it. I'm going to give the answer directly after this. So if you don't want to see the answer, just pause the video and work through it on your own and then hit play again and you'll see the answer. So formulate a 20-10-10 using urea, DAP, and SOP. Now you need to know urea is a 4600, DAP is an 1846, and SOP, which is sulfate of potash, is a 0050. Now you're going to need to know that. And if you don't know that, you're not going to be able to solve these problems. So if you don't know that, just Google it, or you can search it and what's the percentage K2O and sulfate of potash and so forth. Or you can figure it out stoichiometrically if you know the analyses of the formula of the element itself or the molecule itself. So this is what the problem number 3 is. Formulate a 20-10-10, urea, DAP, and SOP. So the answer to this and how to do that isn't coming up now. So pause this if you don't want to see it. So the answer is 20-10-10 is 700 pounds of urea, 434 pounds of DAP, 400 pounds of SOP, and then 466 pounds of filler. So it's easy to get the answer, but how did we do this? How did we get to this point? So we're going to walk through how we did this. How did we formulate this fertilizer? Okay, Step-by-step answers to number 3. A 10 times 20 is 200 pounds of P2O5. Remember, it was a 20-10-10. So 10 times 20 is 200 pounds of P2O5 divided by 0.46, which is the percent P2O5 in DAP. And you come up with 434 pounds of DAP. You then take that 434 pounds, divide it by 18%, and you come up with 78 pounds of nitrogen. You take 20 times 20, and you come up with 400 pounds of nitrogen, which is what we need total. But we have to subtract 78 pounds from DAP, and we come up with 322 pounds of nitrogen remaining. We take that 322 and we divide that by the percent nitrogen in urea, and we come up with 700 pounds of urea. So here's 434 pounds of DAP, 700 pounds of urea. The only thing missing now is the potassium source. We have 10 units of K2O divided or multiplied by 20, 200 pounds of K2O divided by the percent K2O in potassium sulfate, which is 50%. And you come up with 200 divided by 0.5 is 400 pounds. So it's 434 pounds of DAP, 700 pounds of urea, and 400 pounds of SOP. Okay, so that's the way you would do it. I know I went through that pretty quick, but being on a video, I'm hoping that you can pause it or slow it down or just take a second if you need to take a second and, work through it yourself. But those are the processes. Those are the steps that you'd work through in order to determine the formula for any fertilizer really that contains multi-nutrient raw materials. There's some things you're going to have to know. You're going to have to know which nutrients are multi-nutrient or which elements, fertilizer raw materials are multi-nutrient raw materials. And you're going to need to know the concentration of these elements in the raw material itself as well. Okay, so there's some presupposition, or you're going to have to some pre-knowledge you're going to have on that. Okay. Now, the next formula is one of the most common formulas in golf. I don't know how many tons of this can go out over the years. Very, very common and very wasteful, to be honest. But this is the next problem. So formulate a 15-5-15 with 50% slow nitrogen and 2% iron, 2% magnesium, and 2% manganese. This is, I don't know how this came about, but this whole 2 units of iron, 2 units of magnesium, 2 units of manganese, people think somehow that this amount is going to be helpful. I mean, the only thing in there that's going to be helpful is maybe the manganese. Yeah, we know the iron's not going to be useful agronomically. And the magnesium, it's going to remain soluble, but I mean, you're not going to probably ever see a magnesium deficiency alleviated at 2% magnesium applied at 300 pounds per acre. I mean, you're just not going to see this, but regardless, it goes out all the time. So this is the problem. Okay, thanks, Western Master Turf, for letting me know. Yeah, sometimes I'm moving a little at a different speed. This is the problem. So pause it if you don't want to see the answer, because I'm going to go to the answer right now. Oh, you're going to use urea. I'm sorry. You're going to use urea, sulfur-coated urea, diammonium phosphate, sulfate of potash, magnesia, and iron sulfate, and manganese sulfate. So these are the raw materials you must use. Okay. So you're going to need to know that diammonium phosphate contains nitrogen and phosphorus. You're going to need to know that sulfate of potash, magnesia contains potassium and magnesium. And you're going to need to know that this is the only source of magnesium and DAP is the only source of phosphorus. Okay, and you're going to need to know the percent iron and iron sulfate and the percent manganese and manganese sulfate. I'm going to show you all this stuff so you can, again, pause the video and look at the percentages. But if you don't know this stuff, you can just probably Google it and find those percentages. Okay? All right, now the answer. So the answer is 240 pounds of urea, 348 pounds of sulfur-coated urea, 217 pounds of DAP, 440 pounds of SOP, 363 pounds of SPM, 200 pounds of iron sulfate, 160 pounds of manganese sulfate, and 32 pounds of filler for a 15-5-15 with 2 units of iron, 2 units of manganese, and 2 units of magnesium from these sources. That's the only way you can blend it. With those sources, there's no other formula. So it doesn't matter who you buy it from. That's going to be the formula. Okay. So now how do we get there? So in this particular case, when you're dealing with some elements that are quite straightforward and simple, and there's only one raw material in there that's going to contain that, sometimes I'll actually start with those easier ones, like the iron and the manganese. You can just get those done and get them out of the way if you want to do it that way. I'm not sure if that's how I did it on this example, but you can just get these out of the way quickly. I can show you how to do that real quick. But the other ones, you have to account for a number of variables. I didn't do it that way. So here's the answer. This is how you do it. There's a lot of numbers on the screen for those listening, but basically you're going to follow the same steps. N is a 15, 5, 15. So you got 15 times 20 is 300 pounds, 50% slow, 50% quick. P2O5 is 5 times 20 is 100 pounds of P2O5. 15 units of K2O is times 20 is 300 pounds of K2O. So it's the same process. It's just a little bit more complicated. Now, if you start down here, you can see that the iron and the manganese is 2 units and 2 units. So it's going to be 40 pounds of each. And you just have to know that the iron sulfate is 20% iron and manganese sulfate is 25% manganese. And you can come up with the 200 pounds of iron sulfate and 160 pounds of manganese sulfate real quick. That's easy. And then if you move to the magnesium, you do the exact same process. 2 times 20 equals 40. 40 times the percent magnesium in sulfomag is 11% magnesium. You come up with 363 pounds of sulfomag. That's easy too, but that came with 80 pounds of K2O because it's 22% potassium. So then you just move that 80 pounds of K2O up here and subtract that from the 300 pounds of K2O that we need total, and you're going to end up with 220 pounds of remaining K2O that you need to supply from SOP. So you just divide that by 0.5. You come up with 440 pounds of SOP. Okay. And then you're going to do the same thing with phosphorus. You have to do the phosphorus first, and all the nitrogen in DAP is going to be quick. Okay. So you're going to do, good morning, Looney. Or I'm sorry, good evening, Looney. You're going to do 5 times 20 is 100 pounds of P2O5 divided by the percent phosphorus in DAP, which is 46. You're going to have 217 pounds of DAP. And then, that comes with 18% nitrogen. You're going to multiply that 217 times 18. You come up with 40 pounds of nitrogen and subtract that from the 50% of the total just in the quick category, because all this is quick nitrogen. So we need 150 pounds of quick and 150 pounds of slow. You subtract the 40 from the 150 pounds of quick, and you come up with 110 pounds of quick nitrogen and divide that by the percent nitrogen in urea, and you come up with 240 pounds of urea and 348 pounds of SCU. Okay. So I know that's a lot on the screen. Again, you can pause it, you can slow it down, whatever you want to do, but it's all on there. And it's just a matter of remembering to do the multi-nutrient first and then subtract the secondary nutrient from the remaining total of whatever other element it came with. And when you're dealing with 50% slow and 50% quick, you just got to don't forget that nitrogen from DAP and pretty much any other source, unless it's coated, is going to be subtracted from the quick. Otherwise, if it's coated, subtract it from the slow. Like if it's coated DAP or something, or coated, sulfomag or something, whatever, they have those in nursery. So you would just subtract it from the slow if that's what's required. Okay. So name at least 3 ways that this fairway blend can be made more efficiently. This 15-5-15 that we just blended. I'm going to just go through some examples of how I would make this blend more efficient. One is the iron sulfate is completely useless. I've gone over multiple papers on that, on iron in the soil. There is almost, not quite, but almost a 0% probability that you would see any benefit in the turfgrass from applying granular iron sulfate or any granular iron source except for some chelates in some rare cases. So there's almost 0% chance. So the iron sulfate is complete waste, and it's 200 pounds. It's 4 50-pound bags. So if you bought a ton, 4 of those 50-pound bags is wasted iron sulfate, and that'll stain whatever you spread it on. So this iron sulfate here can be removed and make room for other nutrients that could be more useful in that ton. So this is one way that it could be made more efficient, is just eliminate the iron sulfate. Okay. The 15-5-15, I've gone over this numerous times, but there's very little evidence on anything other than putting greens that applying a 1-to-1 NK is an efficient way to do it. It's effective. You're going to alleviate if there is a potassium deficiency, which I would be skeptical that there is. But if there is, a 1-to-1 NK would alleviate that. It's just that it's very wasteful because there's no evidence to indicate that a 1-to-1 is the efficient way. The evidence we have indicates that a 2-to-1 NK would alleviate the potassium deficiency, and any further additions of potassium is simply wasteful. And so you're burning money, you're wasting money, you're charging your clients more money, or whatever, or you're just losing more profit, or whatever the case is. So this 15-5-15 could be changed to like a 30-0-15 or a 10 or 20-0-10 or 25-10 or whatever the analysis we could formulate. But that's another way that this formula could be made more efficient. Oh, there's my wife in the chat. Good morning or good evening. Okay, so that's one more way that could be made more efficient. Okay, and the one of the other ways is this magnesium source. Magnesium is very rarely beneficial. Okay, it's almost always available in soil solutions or soil extractable. Magnesium is almost always greater than any critical limit that we're comfortable with in the literature. Occasionally, it might pop up, but it's very uncommon to have a magnesium deficiency in turfgrass. And so that could be considered an area that you could eliminate to make this blend more efficient. And then, of course, you could blend it with no filler if you wanted to. Okay, I'm not going to argue the manganese sulfate because there are cases where manganese can be useful. It's limited, but it could happen. Okay, and there's really not a whole point in putting in any of the potassium unless you have a good reason. It's limited, but it could happen. Same thing with phosphorus. Phosphorus deficiencies are very obvious and not particularly that common. But if you know you have an area that's deficient in phosphorus, you're going to know it. It's going to be there. You're going to see it, and then you would have a good reason to continue to apply phosphorus in that area. But if you don't see a phosphorus deficiency year after year after year, you really don't need to apply that phosphorus. There's really not much evidence to support that, and that's also potentially a wasteful. Again, I'm not going to say you would never see a response to phosphorus because you can see a response to phosphorus, but it always comes in cases where phosphorus is deficient. So that's another area that this blend could be made more efficient. Okay. Chuck, yeah, bent grass putting greens. Now this 1-to-1 NK though actually would be an evidence-based approach on putting greens, but on anything other than putting greens, it's not. Thanks for making me laugh, Chuck. Okay. Understanding filler. Now we're going to go into filler. There's a lot of options for filler. There's a lot of agronomically valuable options for filler, but there's also agronomically harmful options of filler. So I want to go through this, and this was actually asked by one of the members on Monday's members only stream. And this is I told you I was either going to do it on Monday or today, and so this is the answer to your question on Monday. I forget who asked that question on Monday morning show. Understanding filler. At the end of this section, you will be able to understand the importance of minimizing filler. You'll understand how to formulate to minimize filler and understand which fillers you should consider when filler is necessary. Okay, so filler, according to the American Association of Plant Food Control Officials, which defines the fertilizer materials, is a substance added to a fertilizer material to provide bulk, prevent caking, or serve some purpose other than providing essential plant nutrients. So these are examples. These are things like sand, limestone, roofing, shingle scraps, stone, rocks, corn husk, sawdust, pretty much anything you can throw in there to take up room in the ton, but not provide nutrients, basically. Okay. There's also filler that does provide nutrients that would be more of like it'd be, in many cases, it can be agronomically beneficial, but you wouldn't label it. You're just going to throw it in there because I'd rather put that in there than limestone or something like that. So, for example, you might have some specific need to apply calcium sulfate, but not calcium carbonate. So you might not want to include like a limestone, even though that's not ag grade limestone. You might not want to include that. You might want to include gypsum instead if that was your specific need. So there may be fillers that do contain nutrients, but are just being added as filler to replace some other filler that you did not necessarily need or want. Okay, it's a bit complicated, but that can happen. Okay, why is filler a concern? Filler can have unintended consequences, both beneficial and harmful. For example, limestone on soil pH. Now, limestone as a filler is not ag grade limestone. It's more like a rock limestone, okay? But over time, depending on the source, I don't know every source of limestone filler, but depending upon that source, it is possible that limestone filler might result in a pH increase. Well, if you don't want that, then that could be a harmful effect. But if you do want that, that might be a beneficial effect. Okay, it just depends on your situation. Other options would be gypsum on salinity. Gypsum is a salt. So if they're adding gypsum as the filler and you're, in New Mexico or you're in, well, that might actually be beneficial if you have sodium issues. But if you don't want to add salt, any excess salt, then you wouldn't want to use gypsum as a filler. But if you had a sulfate deficiency and you didn't have any other form of sulfate in your blend, then you might want to include gypsum as a filler because gypsum is calcium sulfate. Okay, and it has been documented, gypsum has been documented to alleviate sulfate deficiency in turf grasses as well as row crops. Filler is cheap. So why is it a concern? Filler is cheap, but it's not free. You do pay for it. Okay, and filler dilutes the fertilizer. Okay, this may be desired. In some cases, diluting the fertilizer may be desired, but will increase the cost per acre. So let me give an example of where diluting the blend down might actually be desired. Let's say, for example, you're sparging the fertilizer with a pesticide. That when you do that, you're locked in to the labeled rate of that pesticide. It must be applied at X pounds of active ingredient per acre, which means you must apply that fertilizer at 300 pounds per acre or whatever, 290 or 190, whatever the rate is that would result in that amount of AI going out over the acreage. Well, if you want to apply a certain pounds of nitrogen at that set rate of pounds per acre, you're going to have to fidget with the analysis, the nitrogen percentage, such that you hit the right percentage of nitrogen on the tag so that when you put out 300 pounds of nitrogen, you're putting out 1 pound of N. So you might have to intentionally dilute it down a little bit. That might be an example where filler could be beneficial if you're locked in on a sparged pesticide rate. Okay. So the answer, yeah. So there's quite a question in the chat is there enough I'm assuming you're saying diatomaceous earth in blends to be considered filler? Well, when I'm talking about filler, Looney, I'm not talking about like some secondary byproduct or secondary additive that comes with a main product that would dilute the analysis down. I'm talking about a product that's intentionally added as a raw material to a blended fertilizer, and diatomaceous earth could very well be intentionally added as a filler. Okay. Oh, in Western Mass, I think you're the one who has the pH down in the 4s. So pH increase in Massachusetts is more than welcome. Yeah. If you're down in the 4s, I would think you'd very likely be encountering aluminum toxicity, potentially even iron toxicity when you're down that low. But yeah, I wouldn't count on limestone filler being a source of pH increase. Again, it's not ag grade limestone. But it's certainly not going to result in a reduction of pH. If anything, it's going to be nothing, or it's going to result in an increase. So you'd have to do some sort of titration or something to see if it actually, that source of limestone would actually result in an increase. Garden Earth Guy asks, how about ground up tires for a zinc source? I've never heard of ground up tires for a zinc source. It doesn't mean it doesn't exist. But I wouldn't doubt that any sort of non-nutrient or even some nutrient byproducts or raw materials are used. Those might be more in ag. I mean, when you're dealing with turfgrass fertilizers, you're dealing with a little bit more of a refined product because the manner in which it's spread and the desired appearance afterwards. When you're dealing with ag, they're spreading this in out of different machines that aren't going to get clogged up near as easily as some of the machines and spreaders in turfgrass would. So it wouldn't surprise me at all if some sort of tire byproduct is used as a filler somewhere, but I've never heard of that in turfgrass. Okay, back to the filler. Okay, so here is an example of what filler looks like in real life. Okay, this is on the screen here. I have a capsule filled with a 15 fertilizer that I blended ages and ages ago. This might have been when I was still working for the fertilizer company. I can't remember. And it uses urea and sulfur-coated urea, and it uses muriate of potash for the potassium source. Okay, so 50% slow release from SCU and 50% quick from urea. And then 100% potassium from MOP. And then all the filler is limestone. And you can see in here, it looks like a fertilizer. this doesn't really look any different than any other fertilizer you probably spread out 1,000 times, okay? But because filler is not on the label, I suspect, although I don't have any evidence of this, it's just anecdotal, I suspect that most turf managers, including very well-experienced, knowledgeable turf managers, are just simply unaware how much filler is actually in this blend. So when we separate out these raw materials, this is how much filler is in that fertilizer, okay? So now on the screen, we have the same fertilizer on the left, and then we have the exact same fertilizer on the right with all the raw materials separated out. And we see urea here, sulfur-coated urea here. Well, this is probably 30% slow release, and then 2/3 quick release is probably what I did there. And then we have all the potassium from KCl here, and then all of this filler. We're looking at probably 1/3 of the capsule is taken up with limestone filler. This is the exact same fertilizer. I blended this by hand and put it in this capsule, and then this one, I filled the same exact raw materials, the same amount. I just separated them out, and you'll see all the urea, all the sulfur-coated urea is in layers, for those listening, and then KCl is in a layer, and then a limestone and taking up 1/3 of the capsule and a layer. It's like a soil profile is what it looks like if you're familiar with that. So it's the same fertilizer, 15-5-15, with the raw materials separated. Now, all we do now on the next one is a capsule containing the same amount of urea, same amount of sulfur-coated urea, same amount of potassium chloride, but instead of using limestone as filler, we've swapped that out for biosolids, a natural organic filler. Okay. This can be desirable or not, but I'm just giving you an idea that this limestone, if it's not desired, other fillers can be used. Now, in my view, and I'm not a specialist in environmental contaminants, but in my view, this probably would not be desired in many locations now because of the now well-known issues with PFAS in some municipal biosolids, forever chemicals. Okay, I don't know if they're in every natural organic fertilizer, but certainly in some biosolids, there can be elevated levels of polyfluoroalkyl substances that can be a big problem. So this may not be desired in some, but you can choose other natural organics or some other raw material that can take up space in the ton rather than limestone. That's the point. And you still have a 15-0-15. Okay. Yeah. So biosolid filler, you say? Yeah. Eric Lickness. Yeah. I don't know if you have a history with that or if I've mentioned that before, but that is a option. Of course, you could do this with anything, gypsum or whatever. I mean, you could put any filler in there you wanted, but sometimes there can be an agronomic value to the filler. Okay. Now we've switched it. Now we have a 15-0-15, but instead of using urea, we've reformulated the nitrogen and switched it and started using ammonium sulfate. And now on the screen, we see the capsule number 1 and capsule number 4. I'm sorry, capsule number 1 and capsule, how do I erase that? Erasing on side. So capsule number 1 and capsule number 2, these are the same fertilizers. It's just that the urea has been swapped out and ammonium sulfate used instead. And you can see how little limestone filler is now necessary when ammonium sulfate's used. Why? Because ammonium sulfate's only 21% nitrogen and urea is 46% nitrogen. So you need a lot more ammonium sulfate to get the same amount of nitrogen than you do from urea. Okay? This ammonium sulfate comes with sulfate as well, which in the old days might have been like, it's just wasted. But now we realize that sulfate can be deficient and it's actually becoming more and more common. So this may be a more desirable blend, but with ammonium sulfate comes reductions in acidity. So you have to understand how these things kind of play into your favor or against your interests. Okay. Now we look at higher analysis. We're looking at ways to either manage filler, reduce filler, blending with filler. And one way we can reduce the amount of filler. If you don't want to use ammonium sulfate and you want to stick with the urea, sulfur-coated urea, and potassium chloride, is simply increase the analysis. So here we have a 15015, which we started with, and we've just swapped the analysis and made it a 24012 with the same 2/3 quick, 1/3 slow, and then the same potassium chloride. And now we see we went from about a third of the capsule containing filler to maybe, 20% of it, or whatever this is, 15% of the capsule being filler. And all we did was adjust the analysis to a 2-to-1 N/K and increase the concentration of nitrogen and potassium, or nitrogen, not in this case. Okay, and then the last one is no filler at all. This is where we've formulated basically a 2-to-1 N/K. It's a 32015. As urea, sulfur-coated urea, and potassium chloride, it's a 32015. You're going to get essentially the same plant food you're going to get from capsule number 2. You're just going to blend it and concentrate the blend high enough with N/K such that you don't need any filler. You've worked out all the filler out of it completely. Okay? You would just apply this capsule number 6 at half the rate as you would capsule number 2. Obviously, this one, if you want 1 pound, you put it at 300 pounds per acre. On capsule number 6, you'd be closer to 150 pounds per acre to get the same amount of nitrogen. So these are ways that we can manage filler, whether it's swapping the filler out for a nutrient filler, or swapping the nitrogen source out to reduce the amount we need, or adjusting the analysis up to concentrate the amount of nitrogen and potassium that are in the blend. One way or the other, there's ways to manage such that we can remove almost entirely the filler, which again, those are the reasons we're interested in that, is because it's not free. You're still paying for that filler whether you know it or not, and it's taking up room in the blend. So filler formulation options. The best option under normal conditions is simply to eliminate the filler, if you can do that. With 2 N sources, we must balance the 2 N sources so that the analysis is correct and no filler is needed. I'm going to show you how to do that at the end. And you can balance the P or K sources if necessary, if you want to do that. But if you have 2 N sources, you need to know the exact ratio, and I'll show you an equation to do that. This can be difficult. To be honest, it can be a little difficult to understand how to do that on your own. So you can also use filler with value. So you can use gypsum or ag-grade limestone or natural organics or some filler that would be of use to you. You can also just simply over-formulate the N and P and K. You can just simply tell the blender, I'm not sure exactly how to do all this eliminating filler. Just over-formulate the N, P, and K until there's no filler left. Whatever the analysis is what it. Tell them that, and they'll do it. They've done it 1,000 times. This is a little easier to understand. So one way or the other, these are some of the options you can consider when you're dealing with trying to make your blend more efficient. All right, so eliminating filler, method 1, increase the analysis. Use a 2-to-1 N/K and increase the N and K analysis until the ton is full. Pretty straightforward. So here's this capsule. The 15015 becomes a 32015. Both blends spread at 1 pound of nitrogen will have the same number of nitrogen particles per area. Same number of nitrogen particles if it's spread at 1 pound N. Sometimes I get that question, well, there's going to be fewer nitrogen particles. No, you're going to spread the blend at a reduced rate, but the rate is twice as concentrated. So you're going to end up with the same amount of particles per square foot in terms of the nitrogen from both of these, assuming they're applied at 1 pound N because they're coming from the same nitrogen sources. Okay, but you just increase the analysis until there's no filler left. The other option is to replace the filler, just like I mentioned. So 15015 remains a 15015, and both blends spread at 1 pound N will have the same number of N particles per area, same amount. And we're assuming this biosolid is a filler and not a nitrogen or phosphorus containing product. So, okay. And then the last one, which is eliminating filler. This is where it becomes a little bit more complicated. So method number 3 is balancing sources. So I said, just to let you know, I told you this is going to get a little complicated. This is where it starts to get a little complicated. I'm going to go through this and just, it's on a video. Just pause it, okay? If it gets too much, or just skip through it if you want to skip through it. But let me get through here so it's out there, and you guys who are interested in rather, the higher complicated stuff, then it's here for you guys to use if you want it. All right, balancing sources. Use a 2-to-1 N/K and increase the N percentage to between 25 to 30%. Solve the K and P first. So whether it has P or K in it, solve that first and get it out of the way. Now you're dealing with just the nitrogen. Ammonium sulfate, in this case, you have ammonium sulfate and polymer-coated urea. Okay. So the SOP in this case is 15 times 20 is 300 pounds divided by the percent potassium and SOP, and you come up with 600 pounds of SOP. That's easy. Okay, we got that in the bank. But now you got to balance the two nitrogen sources until the ton is full. Now you can sit there on an Excel file and fidget with these back and forth. It'll take you 5 or 10 minutes, but you'll figure it out. You'll fidget with the analysis and fidget with the amounts until you get the exact right amount down. If you want to do that way, that's fine. If you want to get it, exactly right, do it quicker, but it's a little more complicated. Here's I think on the next slide or coming up is the equation, if I'm not mistaken. So here's the SOP. We have 1,400 pounds remaining, and we need 560 pounds of nitrogen. Okay. So we have to provide 560 pounds of nitrogen between two sources, and we have to have the two sources add up to 1,400 pounds, and the two sources have different concentrations of nitrogen. So how do we do that? Here's how we do that. Balancing two sources. These can be two N sources, two K sources, whatever. Two P sources, doesn't matter. Two iron sources. At the end, we're going to show 3 iron sources, and we're going to show how this equation would have worked, but it doesn't work based upon how the raw materials pan out. So here's the equation. This right here is the percent nitrogen as on ammonium sulfate. I'm not going to be able to explain this to those listening. I'm sorry. This is visual here. The equation is relatively straightforward, but it can be complicated. So you take the percent nitrogen in ammonium sulfate, and you're going to multiply that by X. I'm going to explain what X is now. X is the pounds of ammonium sulfate. Okay, percent in ammonium sulfate times X. Those are in brackets. Then you're going to add that to another bracket, which is the percent in polymer-coated urea, which are the two N sources we're trying to manipulate. Percent in polymer-coated urea, which is multiplied by the pounds in the ton remaining minus X. And then the 560 at the end is the pounds of N, the total pounds of N that's required. So through this equation, it will give you the exact number of ammonium sulfate. What we need to do is solve for X. So solve for how many pounds of ammonium sulfate we need, and then the remaining is going to be its polymer-coated urea. But I'm not particularly smart enough to figure that out, so I cheat. And I go to this website called www.mathpapa.com/equation-solver. And you can literally just copy and paste that exact equation that I have on the screen. You can literally copy and paste that into the window. I just did it this morning to make sure it was still active. And it'll spit out the exact number. You don't even have to change anything on this equation. Just copy and paste it directly in MathPapa equation solver, and it'll do it. So copy this equation down if you ever want to just fidget with 2 potassium sources to eliminate the filler, or 2 nitrogen sources to eliminate the filler, or whatever you want to do. Just copy this down, store it in Excel, refill in these percentages and amounts based upon your specific blend, and it'll give you the exact amount. You don't have to fidget with it for 5 or 10 minutes trying to figure it out. And what it'll do, it'll spit out this number, 190 pounds of ammonium sulfate. We had 1,400 pounds remaining. 190 pounds came from ammonium sulfate, so now we know we need 1,210 pounds of polymer-coated urea. And that will be the final analysis. So we have 1,210 pounds of final batch sheet, 1,210 pounds of urea, 190 pounds of ammonium sulfate, 600 pounds of sulfate of potash, and that'll give you 2,000 pounds of a 2805 with no filler, ammonium sulfate, polymer-coated urea, and SOP. So it's not going to give you, that says urea. I think that should say, did I say polymer-coated urea or did I say urea on the original one? Oh, that's polymer-coated urea, 4300. So yeah, this should say, this right here should say polymer-coated urea, not just urea, sorry. So if you want, which is probably is, what is that, 90% slow release, 10% quick release, whatever that comes out to be, 2805 with no filler, right here's the batch sheet. Just copy it down and give it to your blender, and they'll give you a 28015 with no filler at all. Use it that it has ammonium sulfate as a little bit of soluble nitrogen, a whole lot of slow release nitrogen from polymer-coated urea, and then a little bit of SOP. That's not a bad blend. That'll store for a long time. That polymer-coated urea is really nice to use, because if for some reason you have a couple bags left over and you're not going to go out for another 8 weeks or whatever, it's going to keep that blend easily spreadable. So, yeah, so Mike Conroy, so wouldn't the added nutrient cost more than the filler? This can seem That can seem correct on the surface, Mike. It can. I understand why you might say that, because the filler is only $100 a ton or whatever, $150 a ton, whatever it is. And the raw material is whatever, $1,000 a ton, whatever. But remember, we're adding filler that has no nutritional value. And that's taking up room in the ton. Anytime we take up room in the ton with a product that costs money, that does not provide any nutrition, if we increase the cost per acre, because we could have exchanged that space in the ton for something that would have been nutritionally valuable. Okay, and particularly with nitrogen, if you're able to do that with nitrogen, which is what I did here, you're going to reduce the spread rate because you increase the concentration of nitrogen in the ton. Hope that makes sense. So the bag cost will be more expensive, but the acre cost will not. It will be less expensive. And I think it was on Monday or time before, I can't remember. I talked about evaluating or looking at how we perceive cost per bag or cost per ton, cost per pound of nitrogen, and cost per day of response, and so forth. And the cost per bag or cost per ton is the least effective method of actually having fairly comparing fertilizers, because I don't know what's in the bag necessarily in terms of nitrogen. Okay, with the cost per pound of nitrogen, it's apples to apples. Okay, because we're always applying fertilizer on the pounds of nitrogen. So I want to know how much does it cost per pound of nitrogen. Okay, that'd be my answer to that, Mike. So the spread, however, to your point, Mike, if this is your point, if you exchange out the filler and you put in more nitrogen and you keep spreading it at the same rate, then yes, it will cost you more money. You need to spread it at a lower rate because you increase the concentration. Okay? Okay. Now, sometimes filler cannot be eliminated. What are our options? Replace the default filler with a filler containing some agronomic value, which I just mentioned, gypsum, biosolids, whatever else. I'm not a huge fan of using biosolids anymore. I used to be back 15, 20 years ago, before PFAS really became more of a genuine concern. I would like to know more about biosolids and their PFAS contents and their potential environmental concerns around that before I really was too convinced on it. But if I had another option, I probably would use a different option now. In the old days, I would almost never recommend gypsum because it just really wasn't that useful. But back then, sulfur was coming down in the rainfall. It wasn't that big a deal. But nowadays, we do have sulfate deficiencies. So nowadays, it might behoove you to consider using gypsum. If you can't eliminate the filler at all, if you can't eliminate it, it might behoove you to consider adding in a gypsum source to provide that sulfate, particularly if you're not applying any other sulfate source in the fertilizer. Okay. You can also overformulate the NP and K. So I just mentioned that. It adds extra NP and K to fill the ton without altering the analysis. You will pay for that NP and K, but it will not alter the analysis. If you don't want to mess with all this, sometimes it can be complicated. Just increase the nitrogen to around 25 to 30%. Get the NPK ratio to like an 8:1:4 ratio or whatever, 2:01 ratio or whatever. Get the ratio kind of in the ballpark. What I mean by that is a 20:10 or a 22:10 or a 24:2:12 or something. Get it in the ballpark, okay? And then just ask your salesman, overformulate the nitrogen so that there's no filler in the ton. In other words, if you got 20 or 30 pounds left in the ton, don't put in a bunch of filler. Just overformulate the nitrogen. Just add in, just make up the rest of the space in the ton, put in the nitrogen, and move on. That's the easiest way to do that. And of course, you'd have to reduce the spread rate accordingly if you wanted to save money on that, because that, in that case, that blend would cost more per acre if you don't reduce the spread rate. Okay, now formulation problem. We're going to get into a couple problems now. 28,315 without filler, using urea, sulfur-coated urea, concentrated superphosphate, and sulfate of potash. So there is no multi-nutrient material in here. It's only nitrogen is only from urea and sulfur-coated urea. Phosphorus is only from concentrated superphosphate. And SOP is only, or potassium is only from SOP. Good evening, AJ Binkley. Okay. So pause it if you don't want to see the answer, because I'm going to the answer right now. The 28315 with no filler is 806 pounds of sulfur-coated urea, 464 pounds of urea, 130 pounds of concentrated superphosphate, and 600 pounds of sulfate of potash. That's the answer. How did we get there? So one second, I'll get back to that question, Western Mass. I'll get back to it after this. So how do we get to this answer, 28315? The answer's on the screen. Okay, so for those listening, I'll do my best, but it's nitrogen is 28315, 28 times 20, 3 times 20, and 15 times 20 gives us 560 pounds of nitrogen, 60 pounds of P2O5, 300 pounds of K2O. We can easily formulate the potassium and phosphorus because those are the only sources. The only sources are from concentrated superphosphate and sulfate of potash, and we come up with 130 pounds of concentrated superphosphate and 600 pounds of SOP. So that's how much we know we've got that in the bank already. We just took the pounds we need of P2O5 divided by the concentration of phosphorus in concentrated superphosphate, and so forth. So we got that. We have 730 pounds. Is that right? 730, and we have 1,270 pounds left. Okay, so then we use this equation. We know the nitrogen sources are from sulfur-coated urea and urea. We pop this equation in MathPapa/equation, and it'll pop right up. And it gives us 806 pounds of sulfur-coated urea and 464 pounds of urea. If you put those exactly in the blend, you will come up with a 28315 with no filler. Again, not really a bad blend, to be frank. I mean, that's a pretty good blend if you're looking for options and you have a phosphorus deficiency or you have a potassium concern. This particular blend is not too bad to consider, at least. Okay. Reformulation. Now, that's everything I'm going to go over for formulation. Okay. That's a lot. I know I went through it quickly, but now we're going to reformulate 3 fertilizers. Okay. And like I said at the beginning of the show tonight, I've intentionally selected 2 that are difficult, and then one I was asked to reformulate it on email or something. And so I'm going to reformulate that. That one's also difficult. Okay, so I'm going to walk through it and I'm going to show you my assumptions that I have to sometimes make because I can't determine everything in the fertilizer. That's one of the problems because we don't know everything in the fertilizer. But we're going to walk through it. So if you have a fertilizer tag that you're looking to, find out what's in it, or for some reason you want to know what's in some fertilizer tag you see on the internet, this is the way that you can do it. And I'm pretty sure it should be easier than the 3 that I'm going to show. Okay. Let's start with how to do it. So what is reformulation from a label? It's determining the pounds of raw material in a fertilizer from the fertilizer label, which you would think we would be able to do that, right? But you can't always do that. It's not always that easy. Okay, I know they try to protect the consumer, showing us and telling us, what the derived from components are and the percent nitrogen. That's a great information. And in some countries, in some continents, they don't even have any of that information on there. So we're better than some. But you can't always tell everything that's in it because they're not legally required to tell you everything that's in it, particularly when it comes to filler. And particularly when it comes to the amount of certain raw materials, when there's 2 different or 3 different raw materials making up one element, they're not required to tell you what percentage that they used of one raw material to make up that concentration. So for example, if you have iron and you have 3 sources of iron in there, and they're all chelated, it's not going to be very easy to determine what percentage of this particular chelate makes up the total. It's not going to be easy to do that. And in most cases, you're not going to be able to do that. Okay. Just letting you know the limitations we encounter when we're trying to reformulate or back formulate some of these fertilizers. So here's a fertilizer you can buy at Lowe's or Home Depot or wherever. This is the Scott's Turf Builder 3204. You can go buy this, I guess, for any box store, I suppose. And the reason I chose this one is because this breakdown under the total nitrogen is a little bit different, and it's not very clear exactly what which raw materials make up this breakdown. Sometimes it can be very clear. On this bag, it's not. So let's break this bag down and come up with pounds of raw materials that make up this 3204 with 2% iron. So the first thing we're going to do is we're going to start with the potassium because that's going to be the easiest. There's 4 units of potassium. 4 times 20 is 80. 80 divided by the only potassium source in here is potassium sulfate. So that's why it's easy to figure out what this is. The only source is potassium sulfate. We know it's 50% potassium and potassium sulfate. So we take 80 divided by 0.5 and you come up with 160 pounds of SOP. So that much we know is in that fertilizer in a ton. We know that that's definitely accurate. Okay, because there is no other potassium source on the derived from statement down here. You have to be able to look at the derived from statement to be in order to come close to doing this. Now we're going to look at this 2 units of iron. 2 units of iron is right here. Okay. 2 times 2 is 40. I'm sorry, 2 times 20 is 40. 40 divided by the percent iron in the only iron source is iron sucrate. Now, iron sucrate is usually 50% iron. Every now and then you'll see a weird one that's like 55% iron, but I'm just going to use 50. I don't know the raw material, the exact percentage of this raw material that they use, but it's probably 50% iron. So 40 divided by 0.5 is 80. So now we know there's 80 pounds of iron sucrate and 160 pounds of sulfate of potash. That's pretty much a done deal. Pretty confident with that. Okay. The next time, now we got to have to deal with the remaining 3 derived from components, and where they're all nitrogen sources. And this is where it can become rather difficult and sometimes just outright impossible to exactly determine what pounds are in there from a particular derived from when you have 3 or 4 different materials making up the nitrogen. We have a slow release, which is methylene urea, and we have 2 quick releases, ammonium sulfate and urea. Now, with ammonium sulfate, this is the only ammonium source of nitrogen in this fertilizer. And up here, you'll see 4.9% ammoniacal nitrogen. So we're going to use that to our advantage. We know that 32% is nitrogen, 3204. 32 times 20 is 640 pounds of nitrogen. We know we need this much nitrogen. If 4.9% of it is ammoniacal, we do 4.9 times 20, and we know we need 98 pounds of ammoniacal nitrogen. 98 divided by 0.21, which is the percent nitrogen in ammonium sulfate. And you come up with 466 pounds of ammonium sulfate. So that much is, I'm pretty confident that much is true. That much is within a couple pounds. That's correct on these 3 raw materials. Okay. So now we're only left with urea and methylene urea, which you'd think would be fairly simple to figure out. It should be fairly simple to figure out. One's slow and one's quick. But the way they have this labeled is a little bit bizarre. They have urea nitrogen, which is 15.1% nitrogen, urea nitrogen. But both of these are urea sources, methylene urea and urea. Sometimes the percent urea nitrogen here will account for both the slow and the quick release nitrogen sources. But in this one, it doesn't seem to do that. Because below this 15.1%, there's another one that says 11% other water-soluble nitrogen and 1% water-insoluble nitrogen. So I don't know their threshold of water-insoluble or water-soluble nitrogen in that methylene urea. I don't know where they put that number. And oftentimes this can be arbitrarily just chosen by the blender based upon their risk tolerance for being fined when an inspector comes by. Okay, so I don't know exactly what they're going to put those at. But what I'm going to do is I'm going to take this 15.1% urea nitrogen, I'm going to multiply it by 20, I'm going to come up with 302 pounds of urea nitrogen. That's how much I know we need. If we assume all the urea nitrogen is coming from the urea, which it may not be true, but let's assume that that's true for now, we're going to come up with 302 pounds divided by the nitrogen in urea, and we come up with 656 pounds of urea. Okay. 656 pounds of urea. This is assuming that all the urea is accounted for in this 15.1%, which it's not always the case. In fact, I think the next label shows that it's not always the case. Now we take this 12. Now, the only reason I'm doing this 12 here is because they have an asterisk here that says 11% other water-soluble nitrogen, and the same asterisk by 1% water-insoluble nitrogen. And you go down here and read it, it says, contains 9% slowly available nitrogen from methylene diurea, dimethylene triurea, and water-insoluble nitrogen. So I'm assuming that this 11 and 1 is entirely coming from methylene urea, and that 9 units of those 12 units is considered slow, I guess. Could be wrong. But I'm going to assume that this 12 accounts for all the methylene urea, and none of the urea in methylene urea is accounted for in this 15.1%. And I could be wrong. But if I'm right, I put it in yellow because I might be wrong. If I'm right, you're going to come up with 12 times 20 is 240 pounds of nitrogen from methylene urea, and 240 divided by the percent in methylene urea, which is 40%. And you're going to come up with 600 pounds of methylene urea. Again, I put this in yellow because I can't be 100% certain that that's actually correct. Remember when I said at the beginning, I've chosen this because it's difficult. You're not going to run into bags like this that always have 3 sources of nitrogen in them, okay? Usually it's a slow and a quick and that's it, okay? In this one we did. There's 3 different sources. And it's kind of labeled a little funky. It's not exactly entirely clear exactly how much is in this particular blend. But if this is correct, then this would be the batch sheet or the reverse formulation of this fertilizer, and you'd have 38 pounds of filler, which is probably about right for a company the size of Scott's. I mean, they're not going to waste a lot of resources on putting a bunch of filler in fertilizer usually. At least I wouldn't think. I'm assuming that, but okay. So you'd have 466 pounds of ammonium sulfate, 656 pounds of urea, 600 pounds of methylene urea, 160 pounds of sulfate of potash, 80 pounds of iron sucrate, and 38 pounds of filler. So if you want to ask how this fertilizer can be made better, we know with almost 100% certainty, as close to 100% certainty as you can get, that this 80 pounds of iron sucrate is 80 pounds of wasted space in a ton that I'm paying whatever I'm paying for iron sucrate for. We know that that's not necessary because we've done work with iron sucrate multiple times on multiple different turf grasses, not including bent grass putting greens. Thank you for reminding me, Chuck. That wasn't conducted on bent grass putting greens. And we don't ever see a response. The iron in iron sucrate comes from iron oxide, and it's just been ground up and reaggregated with usually molasses or some sort of sucrose or something. And they just spread it back out. It disperses beautifully. I mean, compared to iron oxide, which is like a hard metal granule, iron sucrate disperses like fantastic. But the turfgrass response is essentially zero. I've never seen a response to it. I've actually done extractions with that. You can go back on the channel and look at the iron chapter or the iron month that we went over. And I've done extractions with the APCO, process of extracting nutrients, and I think the amount of soluble nitrogen there was 0.5%. So 99.5% was insoluble. You're not going to see anything from iron sucrate. And then I'm not going to argue the rest of it, the N and K. I mean, you might see a response from the SOP. The chances are it's probably from the sulfate, not the potassium. But the rest of it is what it is. Methylene urea is expensive, but I'm not going to go down those roads right now. Okay. But all in all, it's not the worst blend in the world. And that's how you would reformulate it. Now let's go to a more common fertilizer that we see in lawn care, or at least more common today. That last one's probably the most common. This is the 2406 flagship fertilizer blend from whatever that company's called. I can't remember the name of the company. Sorry. I should, whatever. Yard Mastery. I don't know. I've never dealt with them, but 2406. And this is the tag. Okay, so here's the guaranteed analysis, 2406, and you're going to see 3% iron. You're going to see 0.5% manganese and 0.5% zinc. And then here's the derived from raw materials, polymer-coated urea, biosolids, muriate of potash, ferrous sulfate, ammonium sulfate, iron sucrate, manganese sulfate, iron EDTA, zinc sulfate. So now we have 4 nitrogen sources in this fertilizer. We have polymer-coated urea, urea biosolids, and ammonium sulfate. So this is what I'm saying. Stuff like this can get complicated to reverse formulate. All right. I wish they could just show you the batch sheet on the dang tag and you'd know what's in it. But it gets, I don't know, whatever. Right now it's not required by law, so no one does it. Okay. So here's how we're going to do this. We're going to start, I think I start the easy way. Do I start the easy way? No, I don't. Whatever. We'll get through it. So 24 units of nitrogen times 20, we're going to need 480 pounds of nitrogen. Oh, I do the hard part first, and then I go to the easy way. Okay, so we need 480 pounds of nitrogen. Okay, 2 comes from this right here, this 1.99% ammoniacal. I'm just going to say that's 2%. So 2% times 20, we need 40 pounds from ammoniacal nitrogen. And the reason I chose that is because the other 3 sources, there's no other form of ammoniacal nitrogen in the blends. I guess you have to know that, but there's no other form of ammoniacal nitrogen here. So I can factor that out. We have urea, polymer-coated urea, and biosolids. There's no ammoniacal nitrogen there, so I'm going to use that first and factor that out and get that out of the way. So we need 40 pounds of ammoniacal nitrogen. 40 divided by 0.21 is 190 pounds of ammonium sulfate. That's pretty confident. I'm pretty confident that that's how much is in a ton, 190 pounds of ammonium sulfate of this particular blend. But it's going to get difficult. Now, 21.58 times 20. That comes from here, urea nitrogen. Okay. The urea nitrogen times 20 is 432 pounds of urea nitrogen. We have 2 sources of urea and polymer-coated urea. Okay. Now, 12.48, which is the percent control release nitrogen from polymer-coated urea. 12.48 we know comes from polymer-coated urea. However, this 12.48 can be put anywhere. In other words, you can put, let's say it's probably not 12.48, it's probably 13. It might even be 15. But it can be 2, 3, 4, 6, whatever. It can be whatever. But they'll oftentimes move that percentage down because of the flaws that exist in the inspection and analysis process. So when someone comes by and inspects that fertilizer and they run that on the instrument and they determine, hey, there's only 13% slow release nitrogen, you're saying there's 14, they're going to get fined for that. And it's really not their fault. It's just whether there was settling in the bag or whether the process itself was just, the error in the process itself, or, maybe it was their fault. Maybe they didn't blend it entirely correctly, but there's just a lot of room for error in blending fertilizer. And so oftentimes the blenders will arbitrarily lower that percentage down because they keep getting fined over. And all you gotta do is call them. They probably won't tell you, but I mean, it's not like a secret. Every blender gets fined every week, especially when they're putting out thousands and thousands of tons of fertilizer. This is very, very normal. It's not anything they're doing, nefarious. This is very, very normal to be fined. But they're just trying to reduce their expenses because they keep getting fined and they're doing everything they can do to prevent that. So you know what? Let's just lower that percentage down a little bit. They're not going to lower the percent slow release down. They're just going to lower the point that they're guaranteeing down. So the reason I'm saying all that is not to get complicated. I don't think it's actually 12.4%, but I don't have anything else to go by. So I'm going to go by 12.48%, but understand it's probably not. It's probably 13 or probably 14. I don't know. Okay. So 12.48 times 20 equals 250 pounds of polymer in. So we're going to assume that we need 250 pounds of polymer in. And then the only source of polymer coated in is the polymer coated urea here. And I'm going to assume, again, I don't know the source of polymer coated urea, but I'm going to assume it's a 43%, 43% nitrogen. And it might not be. Okay. It might not be 43% nitrogen. There's polymer coated ureas that are 42 and 41 and 44. Okay, most, today in lawn care, I don't know what polymer coated product Sunnyland uses. They probably use Duration, but I don't know. And all the Durations are 4300. So it's a pretty good bet that it's a 4300, but I can't say for sure. Nor can I say for sure it's exactly 250 pounds they need. So there's a little bit of uncertainty here. But 250 pounds divided by 43% is 581 pounds of polymer-coated urea. Okay, now, we knew we needed 432 pounds of urea nitrogen, and we know we just came up, we determined we already came up with 250 pounds from polymer-coated urea, so the only thing left is 182 pounds of urea nitrogen, and the only source left is from urea, so we take 182 divided by 0.46, and we come up with 395 pounds of urea. So that's how we would do that. There are some assumptions being made. There's probably, whoever blends this fertilizer is going to look at this and go, oh, no, Travis is wrong. Yeah, no, I could very well be wrong. I probably am wrong because I don't know. There's a lot of information here I just can't figure out or determine from the tag. There's no way to know. Okay, and then the last part is the water-insoluble nitrogen. Now, this is something else I don't know. I don't know if they're counting some of the water-insoluble nitrogen from polymer-coated urea, which sometimes that can happen, but more than likely, they're counting on this water-insoluble nitrogen, which is this, well, here on the tag right here, 0.43 water-insoluble nitrogen is probably coming from the biosolid. But I don't know. Nor do I know the source of their biosolid. This company, Sunnyland, I believe, is in the ridge of Florida. I think their plant's somewhere in the south central area of Florida. They're probably getting their biosolid from Tampa or from Jacksonville, but I don't know. However, it's a pretty good bet that the amount of nitrogen in that biosolid is around 5%. Okay, it's probably around 5%. So if that's the case, I would take 0.43 times 20 is 8.6 pounds, and then 8.6 pounds divided by 0.05 would be 172 pounds of biosolids. And I put that in yellow because I can't be certain. There's a lot of room for error here. Okay. I suspect they didn't do this. I said, I'm going to show you at the end what I would have done, and this is probably what they did. But I'm walking through the process of I'm going to be in the ballpark of what's in the ton. Okay, I'm going to be in the ballpark. Some of these, I guarantee, they're dead on, like the ammonium sulfate's dead on. I can guarantee you that's correct. The rest of this, when you're dealing with 3 remaining nitrogen sources, it becomes complicated. You don't even need 3 remaining. I mean, I don't know why they have all this stuff in there, but whatever. Okay, let's go to the easy part. The easy part is the potassium and the remaining part. The potassium is, we need 120 pounds of potassium. How did I get that? I took this 6 and I multiplied it by 20. And then I take 120 pounds and I divide it by the percent potassium in KCl, which is 60%, which is right here. And we come up with 200 pounds of KCl. And the only source of potassium in this fertilizer, as you can see from the derived from over here, is potassium sulfate or muriate of potash. I'm sorry, potassium chloride or muriate of potash right here. Okay. So we know that's correct. That much is guaranteed. We're right on that one. Let's go to the iron. We have 3 units of iron. Right here, we got the 3 units of iron. Multiply that by 20, 60 pounds of iron's in the ton. 60 divided by the percent of iron that's in iron sucrate, which is 50%. And we know we need 120 pounds of iron sucrate. That much, I'm sure, because there's only iron sucrate and iron EDTA in here. Okay? You can do this with... actually, I may not have done... No, I didn't do that. I'm sorry. Yeah, so this 120 pounds of iron sucrate... I guess I made an error. This 0.45, I should have another line here. I guess I could type it in here. I should have another line here that says 0.45 divided by the iron in iron EDTA. Now, some iron EDTA is 10% and some iron EDTA is 14%. So you could, what I would need to do is here, I guess I would write this in here and then say 0.45, which is, I pulled from right here, chelated iron. I made an error here. So, and then you divide that by 0. And I don't know the iron source in iron EDTA that they used, but let's say it's 14%. You'd go divide it by 0.14 and they would equal whatever that equals. So it'd equal 0.45 divided by 0.14 is, no, hang on, 0.4. 3.2, is that right? 3.2 pounds? That doesn't sound right. That might be wrong on that. I'm doing this on the fly here, guys. 3 pounds of EDTA. EDTA. I could be wrong on that. So I left that out and I shouldn't have. So I made an error there. But you'll see here that the majority of the iron is coming from iron sucrate, because only 0.45 is coming from iron chelate, and the rest is coming from the only other source remaining is iron sucrate. Okay, sorry about that. I made an error. Okay, so now we go to the manganese. The manganese is right here, 0.5%. 0.5 times 20 is 10 pounds. 10 pounds divided by the percent manganese in manganese sulfate, which is 31%, comes up with 32 pounds of manganese sulfate. That much is correct. And then we come up to the zinc, which is, I don't know why this is even in there, but whatever. 0.5 times 0.5, it comes from right here, this percent. 0.05, sorry, times 20 is 1 pound of zinc. 1 pound of zinc. I mean, come on. 1 pound of zinc in a ton. Okay, so 1 divided by the percent zinc and zinc sulfate is 35%. You come up with 3.3 pounds of zinc sulfate. So you got 3 pounds, which is basically like a big handful in a huge ton. And then you're going to spread that at, 200 pounds, 250 pounds an acre, whatever it is you're spreading it at. Can you imagine this? You're going to have one particle literally every 500 square feet or whatever. I don't even know what that'd be, but what's the point? It doesn't make any sense, but that's what it would be. Okay. So with the exception of my mistake with iron, you'd add iron EDTA in here. This would be the batch sheet for the 2406 Yard Mastery blend, and it has about 300 pounds of filler in there. Okay, ammonium sulfate, 581 pounds of polymer-coated urea, 395 pounds of urea, 172 pounds of biosol. Now, what I would have done, and this is probably what they did, I don't know, but what I would have done, I wouldn't have added this biosolid in here as a raw material. I would have just taken the filler, which is 307, and the 172 pounds, added these together is 479 pounds. And I would have just put in, 479 pounds of biosolid as the filler. I mean, if that's what you want to do. I mean, I don't know. Maybe they had another reason why they didn't do that, but maybe they did that. And this is, this isn't exactly what they did. Maybe they just added in the biosolid completely and there is no filler in there. But again, this is a relatively difficult blend to reformulate because there's so many nitrogen sources in here, and it's hard to come up with exactly what they did and how they did it because we don't have enough information on the tag. And so as the consumer, I mean, if the intention of the tag is to give the consumer, all the information he needs to make a decision, these tags fail at that because I'm a consumer and I'd like to know what's in there. And 99.9% of the consumers aren't like me. They're not going to care. They're not going to know. But I want to know, and I can't figure it out. This is about as close as I can come to it. Okay, and the last one, which came from a request, I would say who it came from, but honestly, I can't remember. So feature, 600, the feature product. This is a very interesting, blend because it's a as you know, it's a 3 pound or 5 pound bag that you put in water and you spray it out. It's still going to be blended on a ton. But the reason this is very interesting is because it's a very easy to blend, very easy to reformulate, except it contains 10% iron. Now, when I saw this initially, I immediately know, because it says 10% iron, I look at the derived from statement immediately and I see iron EDDHA, iron EDTA, and iron citrate. And I know, just because I've done this a gazillion times, that there's almost no EDDHA in that fertilizer at all. If I was to bet, I'd say there's less than 5 pounds. It's probably less than 1 pound. And the reason I say, and same thing goes for EDTA. And the reason I say that is because you can't get 10% iron in this fertilizer from these sources except from iron citrate. Well, you could get it from iron EDTA, but there would be nothing else in the blend because iron EDTA is 10% iron, or like I say, you can find some that's 14% iron. So if iron EDTA, let's say it's 10% iron, you would have the only thing in the blend would be 10% iron EDTA, and there wouldn't be anything else in it. But we have 6% nitrogen, 1% magnesium, 8% sulfur, and then 2.5% manganese. There's a lot of other things in this fertilizer. So in my opinion, the only way that they're able to do this is to use iron citrate, which varies between like 20% and 22% iron. It just depends on who you're getting the iron citrate from. Okay, I can't say for sure. I don't know the percent iron in the iron citrate raw material that they used. But the vast majority has to come from iron citrate because you physically can't fit everything in the ton by using the other two iron sources. And I'm going to show you what I'm talking about here in a second as we blend this up. I'm going to do all the easy stuff first, I believe, in this one. So the nitrogen times 20 is 120 pounds of nitrogen. 120, the only source of nitrogen is right here, ammonium sulfate. The only source of magnesium is magnesium sulfate. The only source of manganese is manganese citrate. So these are going to be easy. So the only source of the only source of nitrogen is ammonium sulfate. So we take 120 pounds divided by 21% and come with 571 pounds of ammonium sulfate. That's done. That's a slam dunk. Now we go to the magnesium. There's only 1 unit of magnesium times 20 pounds of magnesium. And the only source is magnesium sulfate, which is 10% or sometimes 11%. Say 20 divided by 0.1 is 200 pounds of magnesium sulfate. So that's a done deal. Okay, let's go to manganese. Manganese was 2.5% on that bag times 20 is 50 pounds of manganese. 50 manganese manganese citrate, again, depending on the source of manganese citrate, it's going to be 22% usually. It can be higher, but that's not the manganese citrates that we would generally use in these sorts of situations. You have to use manganese citrate, heptahydrate, and I'm pretty certain that it's 22% manganese. Anyway, so 2.5 times 20 is 50 pounds of manganese. 50 divided by 0.22, which is 22% manganese and manganese citrate. You come with 227 pounds of manganese citrate. So you add these all up, you're going to come up with whatever you come up with, 998 pounds already taken up in the ton. So there's only 1,000 pounds left. So with only 1,000 pounds left, you can't use EDDHA because it's only EDDHA is only 5 or 6% iron. And you can't use EDTA because EDTA is 10 or 14% iron. So if you filled up the entire remaining amount with EDTA, it wouldn't be 10% iron, which is what's guaranteed on the tag. So you know right there, it has to be almost entirely iron citrate. So when we look at it, 10%, 10 units of iron is 200 pounds of iron in this ton. Well, iron citrate, I'm going to assume that they use the iron citrate that's 20% iron. If you do 200 divided by 0.2, you're going to come up with, that doesn't look right. Hang on. 200. Yeah, that's right. 200 pounds of iron divided by 0.2 or 20% of iron in iron citrate, you're going to come up with 1,000 pounds of iron citrate. So now we're at 1,998 pounds in the ton, and we still have two forms of iron left. The iron EDTA, remember the iron EDTA is on the blend. And the iron EDDHA is on the derived from too. And there's only 2 pounds left. So we already have 1,998 pounds in the ton without the EDTA and the EDDHA, and we still have to put those in somewhere. So how do we do it? We cannot formulate the iron with EDTA and EDDHA because they have 14% and 6% iron respectively. It can't be done. So how do we do it? We just add 1 pound of each. And that's it. In other words, you don't have to, you could probably add in 0.1 pounds of any raw material and it'll show up on the derived from statement. So that to me, the formulation is somewhere in this ballpark. 571 pounds of ammonium sulfate, 200 pounds of magnesium sulfate, 227 pounds of manganese citrate, 1,000 pounds of iron citrate. And then if you add 1 pound of iron EDTA and 1 pound of iron EDDHA, it'll show up on that tag. And you got 2,000 pounds of 600. So that's some of the tricks. I'm not saying that this particular company did this because I could be completely wrong, but I know I'm not wrong on ammonium sulfate, magnesium sulfate, manganese citrate, but these 3 iron sources, I don't see how you could put any amount of EDTA and EDDHA in there that's any meaningful amount. I don't see how you could do that. But these are little tricks that blenders can use to have a raw material that might be valuable show up on the tag when in reality there's almost none in the fertilizer at all. and I'm just speaking from experience. For those of you who might not know, I blended, fertilizers for 6 years or more, or whatever it was, 6 or 7 years. You put 1 pound in there, it'll show up. I think you could probably put 0.1 pounds in there and it'll still show up on the derived from statement. So if you want iron EDTA in your granular fertilizer, I could put 0.1 pounds and it'll show up as iron EDTA, EDDHA or whatever. And if you put in another iron chelate in there, like a less valuable iron chelate, it'll just say iron chelate. It won't tell you how much EDDHA or the other chelates actually in the fertilizer because they're all grouped under the same category of just iron chelate. Just like this tag. Let's go back to the tag. You'll see right here, iron chelate, 10% iron, 10% iron chelate. That's all it says. It doesn't tell you what percentage or how much of these more valuable, like iron EDDHA is like $70,000 a ton or whatever. I mean, it's been years since I priced that, but it's insanely expensive. And it is one of the few chelates that is, for practical purposes, immune to the effects of pH. It's going to remain soluble at virtually any pH you'd ever encounter in agriculture. So it's very valuable. So I would want to know as a consumer, well, how much is actually in that fertilizer? I mean, it'd be nice to know that. But I have a very strong suspicion, and I'm pretty confident that there's virtually none in that fertilizer. There's just enough for it to show up on the derived from statement. And the majority is from iron citrate. And there's nothing wrong with iron citrate, particularly because you're spraying this out. Iron citrate's not a soil chelate. It's not going to maintain any solubility in the soil. And I've shown the data on the channel to back that up. So iron citrate's not going to help you at all when it hits the soil, but it will help you a lot when it comes to avoiding staining. If you've ever stained concrete or pool decks or cart paths or anything like that, that will definitely be your friend in that case. It's not going to be a chelate when it hits the soil though. Okay. But if you're going to spray this out, which is what this is a sprayable product, spray it out, say, 10 to 20 gallons per acre. So it sticks on the leaf, spray this out. It'll stay on the leaf as iron citrate. It's not going to stain anything and probably be just fine. But they put these other ones in there to make it look more valuable than it actually is, in my opinion. Anyway, that was fun. That was fun blending that one. I've never reformulated that one, but I knew immediately that there was something off when I saw 10% iron in these iron sources. There's no way to do that without the majority coming from iron citrate. It's the highest concentration of iron is coming from iron citrate, and it's one of the only ones that's greater than 10. So, anyway, that was interesting. I found that informative. So whoever asked me to do that, thank you. I would not have reformulated that one, but it definitely shows some interesting kind of behind the scenes sort of tricks that people can do to to make a product seem very valuable when in fact it is probably a perfectly fine product, but as far as the value of EDDHA and EDTA, I doubt there's much value in that particular blend at all. Now, this is the last episode for fertilizers for probably a while. On Monday morning, members only show is where I'm going to start the same process that I've just gone over the last 3 or 4 weeks. I'm going to start that with soil testing. Members only, Monday, 10 a.m. It's going to be a presentation. I think I usually give like a 1 or 2 hour presentation, but a year or two ago I went to where I was, Arizona somewhere. And I give a 4-hour presentation on soil testing. And so I'm going to break that down in 1 hour segments. And I'm going to go over that presentation, some of the information you've probably already seen on the channel, but I'm going to use that and I'm going to show all that presentation to over 2 or 3 episodes, whatever it takes. And then after that, which is probably in the middle of July sometime or 1st of July sometime, I'm going to then go back to my normal format of PDFs, but I'm going to focus on soil testing PDFs, soil testing scientific articles. Okay, so look, that's what I would look forward to for the next several weeks. So presentation for the next 2 or 3 or 4 episodes, and then go back to articles. Okay, guys? I don't see any questions in the chat. Oh, thanks, Chuck, for gifting membership. Oh, to Jeremy Bosch. He'll be appreciative of that. Thanks so much, Chuck. I appreciate that. All right, guys, Monday morning, members only show. If you want to be a member on the phone, it's a different button. There is no button, I think, to join on the phone. I think you have to go to the computer or a tablet to actually join to be a member. Sometimes I get that question. And you can join the members only show. Remember, it shows up as a on the community tab, on the members only community tab. Don't forget, check that throughout the weekend. I'll post the link to the members only show under the members only community tab. Okay, guys? Okay, well, hang on. So reminder, okay, I told Western Mass I was going to answer this question. Thanks for reminding me. Reminder, 60-40 quick slow fertilizer on 90 degrees on cool season turf. What was the question? Let me go back to your question. When you asked that, Western Mass, let me see here. You asked that back at the beginning, and I said I was going to answer that, and I failed to. I'm sorry. Oh, okay. My take on using a 60-40 quick slow release on cool season turf in 90 degree plus weather. Well, why would I'd have to know more. Why would you be doing that? That'd be my take. You want to apply, is this you want to apply a 60-40 quick slow on cool season grass basically now in the summer in July? I would say exercise caution, a lot of caution if that's what you want to do. I don't really I'm not so delicate around applying nitrogen to cool season grasses in towards the last part of May and into June. I'm okay with that. I think the turf grass usually responds well if it has a little bit of food, but I wouldn't be out pushing it in the middle of the summer at all. But if you choose to go out with that, I'd be going out at very low rates, and I would be in control of the water. I would want to make sure that I get that watered in. I'm in Kentucky, so if I'm doing that, let's say I'm putting out 60-40 on Kentucky bluegrass or tall fescue in the middle of July. I wouldn't do that. But if I did do that, it'd probably be like a quarter pound in or a third of a pound in, or maybe a half pound in if I got daring. But I would do that only on locations where I could control the irrigation and make sure I got that watered in. Yeah. I'm not sure exactly where you're going with that, Western Mass, but it can be done. I'm not opposed to it, but I personally wouldn't do it. But if you had to, I'd make sure you water it in and go at low rates. That'd be my take on that. Thanks, guys and gals. I appreciate everybody's input. Thanks so much. I really appreciate all the members and all you guys watching. I'm still surprised anybody watches this thing. So it keeps me encouraged, keeps me coming back. See you guys on Monday morning, members only, 10 a.m. Have a good weekend.